Hello and welcome back. My name is Manny. As you can see, we're coming to you from the downtown business district. Today's topic is the test of variance. This is presentation 810, test of variance. This material is in your textbook, pages 499, and your workbook, page 826. We want to acknowledge the development team of Brad, Spencer, and Amanda. And firstly, why a test of variance? Variance is a standard measure of the variability of data, and a large variance generally means uncertainty. The less the variance, the greater predictability. The examples are drug potency. The greater the variance in potency, the more harmful it might be or more ineffective. Stock prices and volatility, tread wear and uncertainty, altimeter readings of aircraft, and uncertainty in that regard. On the positive side, genetic variability tends to be considered a good feature as it tends to ensure adaptability and variation of species. And so we're going to look at an example in the pharmaceutical industry where a company official states that the potency of its drug varies from its stated mean by plus or minus 0.12 milligrams per cc with 95% confidence. And that becomes the test we're going to carry out. Now this is a test of variability. Let's see what it means. If this is the population X, we're looking for a 95% confidence interval for X, and this means an error of plus or minus 0.12 as stated in the problem, and this corresponds to plus or minus 1.9 sigma, and this results in the equation. These two things in the yellow must be equal. Solving for sigma is saying that sigma is plus or minus 0.061, and this becomes the 68% confidence region of the mean. To test the claim, we take 15 vials. Here's our data here. Here's our sample mean, and here's our standard deviation. So we're going to test if the degree of difference between these two estimates of sigma proclaimed to be 0.061, our results 0.16 milligrams per cc. No hypotheses, there's no significant difference. The alternative is that the standard deviation is significantly above. Note that we're not concerned with the standard deviation being lower because that means generally more certainty. The test for this test, the test statistic is called the chi-square, degrees of freedom n-1. The curve generally looks like this, and we're saying that on average when S and sigma are equal, or approximately the same, this chi-square will be equal to n-1 because this will be, S over sigma will be almost 1. And then the mean or average, the chi-square, will be around 14. Now we're going to look at the table because we're looking at a critical region here. When S becomes sufficiently great, this chi-square will become critically large. If, for example, we're going to look at the critical value, degrees of freedom 14, with a one-tail value of 0.05, the critical value 23.648 gives rise to the rejection region, and the failure to reject a critical value of chi-square 23.685. Now let's look at the evidence. The evidence is by way of S, which is in the table up here, our sample data. 0.16 versus 0.061 gives a chi-square value of 96 compared to the critical value 23.685. This is sufficient evidence to reject H0. The p-value is, and understand here we go across this row, degrees of freedom 14, attempt to find 96.32, and you can see is well beyond the table here, which suggests that the p-value is on the far end here. It's much less than 0.005. Overwhelming evidence against H0. Action, remove drug from the market. Well, that concludes presentation 810. We ask you to review once again, take notes as required, and when finished, go to presentation 811.